is over, and we are meeting after this. Wednesday is a holiday, 26th of January, and our next class is on Friday. So Friday will be a revision kind of thing. I will take up some of the leftovers. But Monday I want to conduct the quiz. How about the quiz, Professor Sen Gupta? What is your opinion? Monday I'm going to conduct quiz for your PRP also, and the same thing I can do for these people in their class hour itself. I'll take their quiz number 1. Okay?
Okay.
So it will be MCQ type questions, but you will have to work out something before you answer. Okay, it will not be straightforward tick mark or so, because unless you experience the procedure of solving some kind of problems or so, I think you cannot consider yourself as properly trained in the class. So that's why the MCQ question will require this kind of some workout, etc. Try to write yourself, don't worry for that, because we are going to have 5 quizzes. It will compensate this way or that way, but make your own attempts. Fine. So now I'm starting because the other boys are going very slow rate. So I start now, Professor Gupta.
Sir, actually, should I, will I keep a one notice for first quiz?
You can put the notice. I have announced in the class. You can send mail to all boys, all sections, that Monday in their class hour, next Monday, 31st January, we'll be having quiz number 1. So that way both the classes are running parallel. Parallel they are running. So on Monday, by Friday, both the classes will be completing 6 hours or so. Sometimes I think 6 or 7 hours. I think 7 hours of the lecture will be completed on Friday, and Monday I will be taking exams for both of them. Okay.
Okay, sir. I am making the
make a notice now. So others should not say that they were not informed. And similarly, all other center teachers will also be informed that they will have to conduct they have to write, create some kind of assignment file for their students, and all the answers will be submitted in that. Okay, so that way it will be easy for them. MCQ type, I'll try to make it form kind of thing, but your help will be needed. Otherwise, normally I put the question on the display and students write by that. They can copy, they can do whatever they want, but the question is displayed and they start writing the answers that way. So if you need to make a form or so, I may need your help there, because mathematical symbols I cannot put over there. Okay. So that is the thing. So fine. So next Monday there is a test now. Now coming to the class now. I'll take the presentation. Yeah, well, I was talking of the response earlier. I did for step input. Professor Gupta talked in very detail. I just summarized that. If it was sinusoidal one, if it was step 1, how does it behave? Pulse, I think both of us have done like that. Only thing was about the your slope when your what to call ramp kind of input is there, input voltage is there, and it is your exponential input is there. So that way I would like to say, when I say exponential input, my Vi I consider here as exponentially decaying function. So this VIT that will be applied to my circuit in both the cases, low pass or high pass, it will be this constant voltage V, it will be decreasing with respect to time. So e to the power minus AT. So this becomes my input, and this input will be given in one case to the high pass, here, and this will be my V naught T. Just see that. This V naught T I'll be interested in measuring. This will be my VIT, like that. You know, you can make it that network, your node analysis or something like that, you can solve it. But here, for your convenience, the VIT for the exponential case and the VIT for the ramp, it will be something different. That is your alpha into T. See, the ramp will not respond well in case of the low pass circuit. That's what I want to show by this. Here is resistance. Here is the integrator, the capacitor. This is my V naught T. And this is my VIT. In both cases, exponential input is this, and your ramp is like this. Alpha is some positive. Negative ramp normally we, okay, I don't want to put for this kind of capacitor your analysis or so. Only positive ramp I'll be considering. So here what happens, in the first case, what will be my V naught T? VIT minus V naught T is the voltage across the capacitor, and that one is your 1 by C integral I dt. Okay, it is true for both, for your ramp as well as for your exponential I dt. I'm talking of high pass case. High pass case. Okay. To solve this integration is coming. I'll convert that into differentiation, because integration will be requiring some kind of constant of integration and all that, and will be unnecessary, will be in trouble. So here it will be your VIT minus V naught T can be written as 1 by C. What is my I? I is how much? V naught T by R into dt. Okay, in case high pass filter, it's so simple to write that way, and then I write the differentiation d dt of VIT equal to 1 by RC V naught T plus d dt of V naught T. Okay, you have to solve for V naught T. You know how to solve the differential equation. You can solve it. D dt of VIT in case of your exponential case will be what? It will be e to the power at. A into e to the power minus at will be your d dt of VIT. Okay, because we assume the voltage, exponential decaying voltage like that. D dt of V naught T and V naught T are appearing. This is a constant multiplying this function. So you can solve this differential equation when this function is known. So I think first order differential equation, all of you are knowing, is the first order differential equation, because it will be A into e to the power minus at. If I differentiate with respect to time t, something like that, A e to the power minus at. Okay, this becomes your something like term used for your integrating factor or something like that, or in some books it is a particular integral is written. That way it will be helping over there. So V naught T can be solved by that, and expression, final expression, Professor Gupta has given over there. My problem was what happens to low pass filter case. Okay. In case of the ramp, this will become your alpha. It will be constant here. In case of your ramp voltage, this will be nothing but this is your alpha. Vi equal to alpha t, so becomes your alpha. Solve the differential equation taking this as a constant. In this case, it is not a constant. In this case, it is a constant. That is the difference between the two, and HPF will work for both the cases. Okay, now I want to put this one. Is there any doubt or question or so? I want to put it for low pass filter case. This thing, same thing, ramp and exponential input I am giving. This is my VIT. This is my V naught T now, which will be exponentially rising. Okay. This is my V naught T. This is my R. So how do I write the equation? V naught T will be capacitor will be equal to integral 1 by C current flowing through this into dt. What is I? Equal to 1 by C integral I is your VIT minus V naught T or VCT, whatever is there, minus V naught T divided by R and dt. Okay, so this will turn out to be, any question? 1 by C dVIT, so 1 by CR, RC it becomes. So V naught T is 1 by CR, okay, into VIT okay. Now differentiation is not there, just see, plus or minus V naught T by RC or CR. This will be taken to left hand side, it will become V naught T outside, so 1 plus 1 by RC will be equal to 1 by RC VIT. So you can solve it, if substitute for the VIT, this thing, exponentially decaying function. Okay, you'll be getting some output, exponential output. But if you are applying the ramp here, VIT applies as the ramp will be here, this not differentiated, so it will be alpha into T. With respect to time, it will keep on rising. So V naught T will be rising to infinity until unless some kind of ceiling limit is put for T. Okay, so ramp in low pass case must be worked out with some kind of ceiling limit on the T. T equal to tau or T equal to capital T, it should become 0. Ramp value should become 0, it becomes sawtooth. Only then you are able to analyze that. Otherwise, ramp or low pass case, you cannot analyze that. It becomes infinite. But exponential input, yes, you can do that. Even if you are not differentiating, 1 by CR into V 1 minus e to the minus AT, if you are putting, there is a solution for that, the differential equation. Is a differential equation coming anywhere? Here, I have integrated, so you are getting this thing equal to d dt of V naught T. So V naught T is getting differentiated. You have to solve for V naught T. VIT will be just exponential input, or it is your ramp. So for the ramp case, it will keep on increasing out to whatever differentiation law you put, it will keep on increasing with respect to time because the input is increasing. The driving voltage is increasing. Is it okay now? In the two cases, is it understood now? So differentiation plays the role. This thing, dt of that b naught. Fine. No question, I hope, because it was done in detail also. I have just summarized that for your convenience. Now I'm coming to something which is there in your syllabus. It is not very difficult thing, simple thing. So here what happens? Low pass filter I can use as integrator. So input to low pass filter, if some voltage is given, output will be integrated form of that, and if it is high pass filter, it will be differentiator. Okay, so this you already know. I will work out with a virtual ground kind of connection. I think it will be analyzed. Exponential function can be taken as a differentiation or something like that. I think for other cases also, I'll do it with the help of the operational amplifier. This is the operational amplifier. Here is the inverting terminal. Here is the non-inverting terminal. This one will be given to the ground. This something else R. I want to make RC, low pass filter. This is my R. This is my C. You already know. I'm taking from the negative. Why I'm not taking from the inverting? This question will be facing in the YY. Why always I'm taking from the negative and put a feedback like that? If I take from the inverting terminal, what will happen? If I take inverting terminal feedback, it will be a positive feedback. Okay? And it will start giving some kind of oscillations. So your output will be distorted by some kind of internal oscillation also. So this one is kept grounded. We are using non-inverting because negative feedback, it will become stable. That is the one. Anyway, here I am giving my VIT. Circuit is this and this are at the same potential. This potential is zero because op-amp is getting zero current. So it is ground potential. This is also ground potential, but two are not short circuited. Okay, it's going like that. Equivalent form, if you want to make, equivalent form will be the your resistance. Okay, this is your capacitance. Here is your actual ground, and here there is virtual ground, but not connected. These are not connected, but the two are coming at the same point. Okay, like that. I'm taking the output here. I'm taking the input here. Okay, this you can realize because this is grounded. I can put as a ground. So this R and C will be going to the ground from the output terminal. I do the same thing anyway. There I'm not doing. As I'm putting this, you already know that. So what is the V naught now? V naught T will be VIT by R will be the current. 1 by C will be the multiplying factor for making that. Sorry, not this, I read it wrong. 1 by C integral VIT by R is I dt. So it will be equal to 1 by RC integration of VIT. So your input is getting integrated if you are low pass circuit. These are there in your syllabus, that's why I have uttered it. In the module 1 it was mentioned. Okay. Now question is when it becomes a perfect integral or perfect integration. Okay. So sometimes it will become your exponential output. Okay. To avoid that, a very large resistance 1 mega ohm range, few mega ohm, 1 mega ohm are greater than that. It should be greater than 1 mega ohm resistance put over there. Then it will be a linear kind of your integration. Okay. So sometimes the exponential term is coming so by putting 1 mega ohm resistance here, very large resistance here. So putting open circuit, I'm putting resistance here, it becomes linear. You think of it, how does it play the role? Because it becomes a parallel combination of RC and that will compensate for that kind of exponential bending in the integrated output. For example, if you're giving a step or you're giving a pulse, it will become a ramp. So it becomes a sawtooth like that. So if you're putting this like that, you get this sawtooth type of thing up here. Otherwise, it will be some kind of exponential. Instead of making a sawtooth, it will go like that. It comes like that. Here, by making this arrangement, I'm going like this, I'm coming like this. When the pulse is applied. So by the your integrator, low pass filter as an integrator. Now coming to the high pass case. Any question here? This I think you have done that in your sometimes your first year this thing. Basic electronics also teacher must have given you. But anyway, I'm putting that. Logarithmic and all that I'm not going because that is a part of your basic electronics. Here differentiation integration was given. So I'm putting that. Now high pass filter becomes the differentiator. Okay, so here what happens? Here there is a capacitor and the resistance goes to the ground. Here virtual ground will be there like this. That is the op amp. Feedback is the resistance here now. R and C. I'm giving my VI here. Here is my V naught T. Okay, so here what happens? What is my V naught T? Is your same thing. I by R. I is the current flowing through the capacitor. Okay, and what is I? One by through the capacitor. V naught T. IT is there. Sorry, R into V naught is there. Sorry, I think I have given wrong. IT is V naught by R. Sorry. Minus IT is V naught by R because current will flow like that. Here is negative. Here is ground. Here is negative. So current will be flowing like that. V naught will be negative like that. Okay. V naught is negative. V naught by R. Because minus V naught by R we can say. V naught is negative anyway. Okay. Let it be plus. No problem. V naught T by R is your IT. Okay. And what is my VIT? VIT is nothing but 1 by C integral I dt plus V naught t. Okay, Vit equal to 1 by C integral I dt, this one, and V naught t, sorry, this is going to be 0 minus V naught t, sorry, plus V naught t minus V naught t. V naught is negative there, it will be your minus V naught t, sorry. Is it okay or not? Let me draw the circuit. I'm myself getting some kind of doubt. Here is your minus, here is your plus. Here I put a capacitance, here I put a resistance. It becomes, this is your ground, for example. This is my VIT. This is my V naught T. This is my ground. So V naught T is negative potential. So this plus this VIT plus V naught T is the voltage difference between here to here. Okay, fine. I think that now I got it. Some mistake was there. VIT. Okay. V naught T by VIT is how much? Let me put that this way. I've got V naught T equal to minus I into R. Okay, because the ground, so ground 2 is going, so V naught T is minus I into R, and your I is equal to, I will be given by V naught T equal to I into R. VIT will be the voltage around across the capacitor. Okay, so VIT equal to 1 by C integral I dt. IT, in fact, IT is time varying, I dt. Okay, so it is like this. So I can put here VIT equal to 1 by C integral V naught T by R with a negative sign here. So VIT is 1 by C V naught T by R. Now I want to find out what is my V naught T. So I have to differentiate that. D dt of VIT, okay, will be equal to minus 1 by RC V naught T. Okay, minus 1 by I is your 1 by RC into V naught T that we have written there. So that means your V naught T for the low pass case becomes minus RC into d dt of VIT. So your input is differentiated, appearing output with a scaling factor minus RC. So it is inverted voltage with the differentiation. This also, if I differentiate, let us say I'm differentiating this thing. I'm putting this kind of signal to my differentiator. What should I get? If I differentiate this one, I should get an impulse here. Get an impulse here. Impulse here. I'll get impulse here. So differentiation comes like that. Okay. So sometimes this is not giving you the delta function. It will be having some kind of, suppose it is exponentially rising sinusoidal signal, for example, is given, that I am differentiating. It will be distorted because of capacitor charging and other things. Okay, exponential charging. So here, once again, in case of differentiator, the high pass circuit, we put a small value resistance, not parallel to the capacitor, but here in series with it. One series, very small resistance in series. Here it was a very large resistance in the parallel, a very small resistance, 100 ohm or so, in series with a capacitor. If you put, your differentiation will be giving a linear relationship between the differentiated output and the input. Okay, so this small resistance helps in high pass filter, improving the linearity. Large resistance helps in your controlling the linearity in the integrator case, low pass filter case. Could I complete that? Or any question is there? This you already know. So what else is remaining? I'm just checking. In the inductor, I'll do while I'm talking about the current sweep generator and voltage sweep generator there. Okay. Something was remaining. What was that? Let me see the syllabus. Yeah, it's here. High pass as a differentiator, low pass as integrator. Attenuators, response to step input, compensated on attenuator, RL, RS. Attenuators, I mean, okay, anyway, that is not nothing. Attenuator, I will talk along with the inductor, that will be better in that case. So, the ringing circuit is again the same thing. The ringing circuit is your, with the help of inductor, to make RLC circuit, and that I will explain. That I am using for the your sweep generator, current sweep particularly. There I'll be talking those things. Okay, so this is a part that RLC and RL network. This module 1 is over. I don't want to confuse you with the help of discussion on the integrator also. Now, what happens in the case of a diode? Anything you want to ask here? I should go to the diode in that case. Diode is not a part of your module 1, but here I wanted to explain that what is happening in the diode, PN junction diode particularly, and that will be used for some kind of your switching circuit.
Sir, excuse me, sir.
Yes.
Sir, could you please upload numericals for some references that in torrent that we don't have numericals, please?
Numericals here. Numericals on this exponential input and all that. You assume any exponential input, R and C value you take, and you just go ahead with that. I'll take example and explain to you maybe on the Friday class or so. I'll take some example, some exponential decaying, fast decaying, or slow decaying, that kind of thing I'll take. I will see what way exponential input is changing. That formula that is given in that book, that I will not be deriving, that you can check yourself to know the differential equation. I said simply that your input is e to the power minus at, a into e to the power minus at. That is the input voltage now, and according to that, your response output will be affected. And for that, already a kind of result has been derived over there. So I will not use that particular expression. I will be using this one, e to the minus at itself, and we go for solving the differential equation and see that. A couple of examples I will take. Similarly, for the ramp, I will not go for the low pass because you know it will be just diverging. Slope will be increasing to infinity if time increases to infinity until that ceiling from some kind of clipping is applied. So that way your exponential input for both the cases will be taught, ramp input for that one. So I think numericals are straightforward. I'll take some 3 or 4 examples on Friday and I'll do that. I think you'll be doing better than that by Friday, I'm sure. So you just do some practice, take up anyone, Milman and top book I am following. There some of the numericals might be difficult for you, but you think of only this part, only response, what way the response is coming. And that part you see, we'll discuss these problems also in the class.
Yes,
Okay, fine. PN junctions, for example, when you are talking about PN junction, here is a P-type material, here is N-type material, P and N, okay? So here you already know, here the holes are in majority, here the electrons are in majority. So if I make a connection, make this one as positive, make this one as negative, voltage like that. So what will happen? We call it a forward bias. Is it taught to you in solid state anywhere?
Yes, sir.
Taught to you? So I need not go in those details. So fine. Or not? Anybody?
Yes, sir, it was taught to us, sir.
It was taught by some solid subject was taught in BTech, isn't it? Not of high school, not in class 12.
Yes, sir. Yes, sir.
Okay, it's fine. So PN junction, it is called forward bias. So here the resistance, we call it RF, is very small. If it is forward bias, the resistance is very small. If I instead of apply minus here and plus here by some other circuit, like that. Forward bias is removed, I am putting this one now. Negative, I am applying to this. So this one negative terminal will repel. Hurry, these are the holes here. So it will repel the holes. Attract the holes, sorry. Attract the holes, it will attract the, positive will attract the electrons, yes. So there cannot be any flow inside the device. Inside the device, there cannot be any flow. I think if you remember the class, it is a kind of thing like that. This is my P-type material. This is my valence band. This is my conduction band. And Fermi level lies here. Okay? N-type material, what happens? It is like that. And here the Fermi level lies near the conduction band. This is my CB. This is my CB. Okay? So when I make a device, the Fermi level coincides. When the PN junction is fused, this Fermi level becomes a straight line like that. When I apply a forward bias, then what happens? This entire band comes down. Okay? Entire band comes down and this entire band goes up. Okay? So what happens? This conduction band and this conduction band is coming now almost in a straight line, not exactly straight line. The difference between this bottom of this and top of this is now decreasing. So if I make like that, current will be increasing in forward bias. It will keep on going up, it will keep on coming down. They will become parallel face to face. That is the maximum current, diode current. So you have got this voltage like that. This is my I, this is my V. It will start increasing exponentially because they have become parallel. CB and CB are becoming face to face. VB and VB, this is VB, sorry. VB and VB are becoming face to face. So this current going exponentially increasing like that. If I apply reverse bias, this will keep on going down. This will keep on going up. What happens? That just separated by more and more energy gap. This bottom and this top is separated more and more, is increased. So in the reverse bias case, what will happen? Here it is like that. Here they separate more and more, so forward current will not flow. Only reverse current will flow because this one will start coming closer to this valence band. Reverse current will flow. So initially it is very small reverse current. It will keep on increasing slightly. And when this CB and this VB become parallel, it will become a breakdown. It is general breakdown. Your ordinary breakdown will be going like that. Okay. In general diode, it is heavily doped. So initially the separation is itself very high. Heavily doped, this is also heavily doped, separation is very high. So in the forward direction, no current will flow for quite some time. And after that, it will start following the ordinary diode. Reverse direction, what happens? Very quickly, this one comes parallel to that. So here, by the time it comes here, it becomes a very large negative current. It becomes a general breakdown, we call it. So that way it is there. And forward bias and reverse bias, these two cases, we are going to use for the switching now. Okay, so the voltage and current relationship for the diode is what? From the diode, forward current is given by reverse saturation current, means this portion. Reverse saturation current is not the breakdown one, I naught into 1 minus it's other way around, sorry. I naught into e to the power electronic charge Q V. V is the voltage applied across this e to the power QV divided by K into this. This V is DC, don't call it AC right now. QV divided by KT, e to the power QV divided by KT minus 1. So this is your I naught. Forward current is coming something like that. So Q is the electronic charge, V is the voltage applied across that, this is the potential across the barrier. So I have applied the forward bias, it becomes like that. If I apply the reverse bias, what will happen? This current will be very small. This will be Q minus V divided by KT. So V is again the reverse bias. This one will be becoming the dominant factor like that. So it will be your anyway, I think I am going too much in the solid state devices right now. Okay, I just close it here. I'll be talking this one when I describe the clipper circuit. And the clipper circuit, this forward current and the reverse current, sometimes you will make some impact on the clipper section. It will not be a very sharp cutoff, sharp switching. At that age, there will be some kind of conduction of the current. So that's why this kind of diode clippers, though we are using, but for very sophisticated operation, that is not a very sharp clipping. Clipping is having some kind of exponential changes at those edges, those corners. Okay, so that I will be describing what way the clipped output will be appearing for the given design using the PN junction. So I'll be talking in the next class. So in the next Friday class, I'll take example and explain. That is, you can have your doubts, etc. for the quiz. Monday will be the quiz. Okay. Question now? Any suggestion? Question Gupta, is it okay? Should we go for the quiz or something else is needed?
Yes, sir, no issue. We can go for the quiz, but as the one student.
I will take some example on Friday because all those models are same.
Thursday class is also there, sir.
Thursday.
Thursday.
Thursday is our class or Thursday is your PRP class? Thursday is PRP class, I think.
No,
only
Thursday,
one
9 o'clock.
Oh, 9 o'clock is our class. Okay, fine. Oh, Thursday 2 hour classes are there. I understand. Okay. 9 o'clock is our class and 4 o'clock is your PRP class. Okay. Thursday there are 2 classes. Friday there is only 1 class. Okay, now I remember. Yeah, Thursday class is there. Very good. So on Thursday I am coming. Okay. But in that case, only 1 period for the discussion. After that, we'll go for the module.
No, Friday is also there.
On the Friday, will go to module 2 in that case.
Okay.
Friday will start module 2 instead of module 1 lingering on there. Module 2 we can go by that. Okay,
Yes, no
students, any suggestion apart from that questions? Okay then, so I can say good day, see you again on
Thank
Thursday.
you, sir.
Okay, all of you. Person Gupta, good. Also, I think we'll see on Thursday in that case. I'll discuss with you on Thursday around 12 o'clock or so about the questions and methodologies.
Okay, sir, no issue.
Okay. Thank you, all of you. Good day.
Good.